Hello, I'm Dr. Harper. This video is in business statistics. It's a lecture video on descriptive statistics. So let's start. Okay, start with the notes on just an overview of what I'll be covering. First of all, the graphs. These are the graphs I'll be covering. And do a frequency distribution, probability distribution, and the probability distribution is also called a density function, a small PDF. And the cumulative probability distribution is called a distribution function, capital PDF. While I'm talking about the measures, I'll talk about the mean, median, and mode, and dispersion, and I'll refer to skewness and kurtosis, but we won't really calculate it. And the bivariate measures, we'll do that later when we look at regression and correlation. Now down below is a summary of a one-word, one-sentence description of each of the graphs I'm covering in this video. So this is what I will be covering, and each one is used for different reasons, different ways, and they represent different things, and that's what we're doing. So let's get started. Okay, first of all, the mean, median, and mode. Consider the mean, median, and mode are three measures of central tendency. Consider the rank order data, 1, 3, 3, 5, and 8. Okay, here's a dot plot, and I've already mentioned a dot plot before, and so now we can see how the asterisks, or the stars, they're the ones that show the actual data, where the data fit along a data axis. Okay, so if we want to calculate the mean, median, and mode, well, first of all, the mean. The mean is the same as an average, same as an expectation. All three of those mean the same thing. No pun intended. The mean and average and expectation are the same thing, if you know what I mean. Okay, anyway, here's the sample, 1, 3, 3, 5, and 8. I probably shouldn't have said that because you probably heard that a million times. That's not a joke anymore. Anyway, 1, 3, 3, 5, and 8. So to get the mean, we take the sum, which is 20, divide by the number in the sum, divided by the number of sum, which is 5, and you have a mean of 4. But notice how I did that. I represented that before in another video. It's the sum over the number in the sum. Well, the sigma x is the sum of the x's. Divided by n, the sum of the x's is going to be 20. Divided by n, which is 5. Well, that sigma, capital sigma x, is the same as taking all of these values, 1, 3, 3, 5, and 8, and dividing by 5. So the sum is 20 over 5, which is 4, and that's the mean. And if that's a sample, it's called a sample mean. Okay, but there's another way to look at it. You can say, well, look, if I look at these the values in the sample, I can define a random variable x. Well, x takes on values 1, 3, 5, and 8. But 1 here occurs one time. But 3 occurs 2 times. So in addition to the random variable, I can say, well, I can have the frequency distribution because 3 occurs 2 times. 5 occurs once and 8 occurs once. So this represents the frequency distribution of the random variable x over this range. So I sum the frequencies, and it's 5, which is the total number in the sum, in the sample. But if I divide through by the sum, then I'll transform the frequencies into probabilities. So this is a frequency distribution. This is a probability distribution. And we've mentioned that before. But now let me go a step further and saying, well, you know, what I can do is multiply the x's times the probabilities. So x times p of x, let's do that. 1 times 0.2, 2 times 0.4, 1 times 0.2, 1 times 0.2, and add those up. Well, that turns out to be the sum of the x's times the probability of x. That represents the mean. But if I consider the random variable 1, 3, 5, and 8, if I consider that a population, then this is the equation for the population mean. Well, notice the population mean and sample mean are the same numbers. The calculations are the same. The only difference is Do I consider this a sample or do I consider it a population? The arithmetic is the same. The number will be the same. It's just how you view the numbers coming at you. It's how you view the data. Is the data from a sample of a population or is the data of the population? That's not really important for a mean because it's done the same way, but it's very important for other measures, which we'll do in this video. So let's go on. Well, to summarize, the average and mean is the same thing. And again, what I just said, I listed it here. X bars the sum over 5, or I could divide through by 5. In other words, 1 times 1/5, 3 times 1/5, 3 times 1/5, 5 times 1/5, 8 times 1/5. But if I do that, then I can collect the 1/5, and that's x times the probability of x. So what I'm showing you here is another way to get that equation. And so the x times the probability of x is the very same. It's just a different way of doing the arithmetic. So it's going to give you the same answer every time. Well, when you have this type of an approach, this is referred to as the expectation of x. So the expectation of x, the mean of x, the average, they all mean the same thing. They're the same number. So the expectation of x, though, is expressed by E of x. E is the expectation of x, which is the sum of the x times the probability of x, which is essentially the same as the mean. So the function p of x is called the probability distribution of x. The function p of x is also called the probability density function of x, because the distribution is the density of the probability distributed over x. And the function p of x is also called the probability measure of x. So we can measure the value of x by the probability that x carries, the value of x carries. Okay, the language commonly used is the random variable x follows the distribution p of x. And it's expressed with that notation. And that is essentially stated as x follows p of x. Now, the main properties of a probability are, first of all, the probability has to range between 0 and 1. It can be below 0, it can be above 1. And the sum of all the probabilities then is 1. Now, if these two conditions are met, that's sufficient to say we have p of x then is defined as a probability distribution. Okay, let's go a little bit deeper. Okay, first of all, the common language used to refer to a mean includes the mean of a distribution, the mean of a random variable, the expectation of a random variable. So the mean, all those mean the same thing. It's a little bit different perspective on when you're talking about an average or a mean or an expectation. Also, the expectation of a random variable can be considered a weighted mean. A weighted mean. Why? Let's back up here. Because when you take an average, essentially each one of these are weighted the same. But what if I weight the 3 here with 2 over 5? Because it happens twice. And so this would be 1/5 and 3 would be 2/5. And that's why this is 0.4 over 5. So that's a weighted mean. And the weights, it's a weighted mean, where the weights are the probability measures of the random variable. So it's really a weighted mean, where you're weighting them with the probability. Well, that's kind of logical, because if something happens more frequent, then that should have greater impact on the mean. Okay. Specifically, the expectation of x, there's the equation, sum of x times p of x, okay, where this is the sum of the random variable times the probability measure of the random variable, okay? And by the way, I just want to make sure that you recognize that if I can put a parenthesis here and then put a parenthesis here, so x and p of x are together. It's not sum of x times the probability. They're together. Same here. I can put a parenthesis here, then I can put a parenthesis out here. In other words, that's one variable. Oops. Let's move that out. There we go. So so then when we talk about the expectation of a random variable, that's the same as a mean. But we're focusing on the random variable part of the equation. When I talk about the mean of a distribution, I'm talking about the probability measure, talking about the measure part of that equation. So you can refer to different parts of the equation, but they all mean the same thing. Okay, now let's go a little bit beyond this course, but also I want to do this just to be complete. The probability measure can be replaced with other measures, such as physical measures like the density, the weight, or the distance. And these applications are used in science and engineering. Now, some of you who've been in engineering or want to go into engineering, this is used quite a bit, or in science. Okay, for example, density. Well, the density of something, the actual balance of something, a density or the weight, could be the balance of it. For example, in here we have 1, 3, 3, 5, and 8, and I could take an 8-inch ruler and have 1, 3, 3, 5, and 8. I put one weight here, 2 weights here, 1 and 1, and that's going to be balanced. And where's the balance point? It's going to be 4. 1, 3, 4 is the balance. It'll balance perfectly. And that's the first, and also down here, what I'm getting at. And that's referred to, in these cases, the expectation operator is called the first moment of the variable. E of x is mu. That's the first moment is the balance point. Okay. If it's distance, it's going to be the center. It's going to be the center of gravity. On and on and on. Okay. Weight, density. You can also have other types of measures, different types of measures: intensity, light, power, force. Okay. Let's go on. It's not a physics course. Variance is commonly defined as the second central moment. Okay. The second refers to the square. The central moment, it's not the moment of x, it's the moment of x about the mean. The second central moment is the moment about the first moment. The first moment is mu. Well, x minus mu then is the central moment. But then the second central moment is the square of that. And so the expectation of the second central moment is referred to as the variance of the distribution. And we'll look at that more in a minute. So again, this is going a little bit beyond the course, but I want to be complete because some people want to know. Other measures can use the standardized expression. We'll take x minus mu over sigma. Now in your statistics course later, in this statistics course later, we'll be talking about this ratio, x minus mu over sigma. If you've had statistics before, you might see that in high school or something, and or other courses, that's the z value. Yes, it is. That's the z. It's a standardized expression. You're standardizing the error, x minus mu, about the variability, sigma, which is the standard deviation. Where the expectation of x is mu, the variance of x is sigma squared. Therefore, the reason they use this standardized expression is the expectation of that expression is 0. The variance of the expression is 1. Okay? So, skewness skewness can be defined a lot of different ways. One way is using the third standardized moment. They take this standardized expression and cube it. That's the third standardized moment. Kurtosis is the fourth standardized moment. Now, we're not going to get into kurtosis in this course. Other applications, kurtosis becomes important, where you're deviating from the kurtosis of a normal distribution. But skewness is important. Skewness just means the slant or the non-symmetry of a distribution. And we will talk about that in here next. Okay. And just after the variance and standard deviation. Okay, well, that's the mean. Okay, the mean expectation, there's a lot there. The mean is a lot more than just taking an average. It has a lot of applications. Okay, the variance and standard deviation. The variance and standard deviation are measures of dispersion, how the distribution is dispersed. Okay, again, I have a dot plot, and here's the mean. And notice the mean 4 here, that's the first moment, that's the central tendency, that's the balance point. And notice that 4 doesn't match up with any of the numbers. So the mean is not another number of the sample or population. It's a measure of central tendency of the numbers. It may or may not be a number in the sample or population. Okay, but then let's take these numbers and let's do a little different approach. Let's do the sum of squared errors about the mean. Okay, well, we've already done that up there. Errors about the mean here is going to be the x minus mu. The error is x minus the mean for each variable of x. But then if I want the sum of the squared errors, I'm going to square it and then sum it. Okay? So let's do it. Let's take the data here, 1, 3, 3, 5, and 8. The mean is 4. Let me take the error about each value. Data 1, 4 is 1 minus 4, and I'm going to square it. I do the same thing for each one of these. And then I sum it up, I get 25. 28. That 28 is the sum of the squared errors of this sample or population. Okay? Now, is it a population or is it a sample? Well, it depends on if it's a population or sample. That's how you call the variance. Here we go. If the data represents a population, then, well, the population size is 5. It's 5 numbers. The population mean is 4. We've done that before. And the population variance is the sum of the squared errors over n, which is 5.6. But if the data represent a sample, then the sample size is 5, the sample mean is 4, the same. But the sample variance, s squared, is over n minus 1, which is 7. So here is the difference between a population variance, you divide by n, sample variance, divide by n minus 1. And the reason you do that is beyond this lecture, but there's properties of the sample variances and population variances. There's properties around these. And these properties, mathematical statistical properties, make a sample variance divided by n minus 1 more useful, more powerful, and easier to interpret. We don't get into that in this lecture. Okay. Now, the sample variance, s squared, is an estimate of the population variance. Okay, and that's part of the properties. In other words, the main property, there's a lot of properties, main property is the sample variance when you have n minus 1 is called an unbiased estimate of the population variance. It can be shown the expectation of s squared is sigma squared. If I take the expectation of this right here, the expectation of this, it can be shown would be sigma squared. And that's a definition of an unbiased estimator. Again, we don't get into that. I've just stated it. And that just means if we take all samples, the population mean of those variances will be the population variance. Okay, that goes into mathematical statistics. We're in business statistics. We don't derive those things in business statistics, but we use them. We use them. Okay, how do we calculate population variance? Aha. When the data set represents a population, then the probability distribution of the random variable can be obtained, and the population mean and population variance can be determined from the distribution. Okay, let's go back and say here's our data, 1, 2, 3, 5, and 8. And let's take the data and let's define a random variable x, 1, 3, 5, and 8. Each one of these has a frequency distribution. Divide through by the total, we have a probability distribution. Now, if we take x times the probability distribution, x times p of x, that's going to be the mean, the expectation of x. But if we take x times the probability of x, okay, that's the expectation of x squared, 21.6. But that is not the variance, but it's close. Because remember, the variance is the expectation of the second central moment. This is not a central moment. Well, the population mean is 4. The population variance is this expectation of x squared. But to transform that to the expectation of the second central moment, you subtract the square of the means of the expectation of x's. So 21.6 minus 4 squared, that gives you the population variance. And so that simple one value minus square of another value, it's very easy to do, especially in Excel. So the population variance, which is the expectation of this second central moment, is 28 over 5, where the mean is the population mean. Okay? Well, 28 over 5 is the same as 5.6. I just gave it as a ratio. Okay, now then, standard deviation. By definition, the standard deviation equals the square root of the variance. That's a definition. Therefore, it follows the population standard deviation is the square root of the population variance. The notation is sigma is the square root of sigma squared. And the sample variance is the square root of sample variance of the sample standard deviation is the square root of the sample variance. The notation S equals the square root of S squared. Okay. Okay, now let's look at some practical applications, more practical. The mean, median, and mode. Here we go. The relationship between the mean, median, and mode and skewness. Okay, I'm not define it. I'll describe skewness. Okay, let the mean be the sum of the x's over n. We know how to do that. The median is called the 50th percentile, or the middle number. The number that's right in the middle. 50th percentile means 50% of the distribution is below that number, 50% is above the number. Okay, 50th percentile. Okay, and that's the median, the value in the middle of the distribution. Now the mode is the value with the maximum frequency. The mode is the value with the greatest frequency. Well, let me illustrate with 3 different samples. Sample A, sample B, sample C. The sample size is 7. Okay, let's look at the values. 3, 4, 6, 6, 6, 8, 9. Well, first of all, the mean is going to be 6. If I add these, okay, I'm going to do the calculations, but the mean is 6. What's the median? Well, there's 3 here. There's 3 here. The middle value is 6. 6 is the median. What's the mode? Well, there's 1, 3. There's 1, 4. There's 3 6s. There's 1, 8. There's 1, 9. So the mode is 6 because it has the highest frequency. So when the mean is equal to the median is equal to the mode, that's referred to as a symmetric distribution. It's nice and symmetric around the mean, which is the median, which is the mode. Okay? But what happens if it's not symmetric? If it's not symmetric, it's skewed. Sample B. Okay, here I go 1, 2, 4, 6, 7, 7, 8. Well, the mean is 5 this time. And the median, well, there's 3 here. There's 3 here because it's rank ordered. It's in order. And the middle is still 6. So I still have the same median as 6, but the mean is different. What's the mode? Well, my mode, there's 2 7s here. There's only 1 1, 1 2, 1 4, 1 6, 2 7s, 1 8. So the mode is going to be 7 because it has a higher frequency. Okay, so therefore, down here, here's the graph of the symmetric. Down here, I have 1, 2, 4, 6, 7, 7, 8. And notice this is skewed left. It's negatively skewed or skewed left. Negative, skewed left, that's the terminology. Well, when it's skewed in that direction, that says I have the mass here, but then I have more values further down here. It's like skewed, it's a skewed distribution. Well, when you have a negatively skewed distribution, the mean is less than the median is less than the mode. That's a clue that it's negatively skewed. Okay, so the median's always a middle number. But if the mean is less, the mean tells you which side the skewness is on. If it's lower, it's left. It's lower, it's negatively skewed. It's left skewed. What happens with sample C? 3, 5, 5, 6, 8, 9, 13. Okay, The mean now is 7. The median is still 6, but the mode down here is going to be 5. Well, in this case, it's positively skewed because in this case, I plotted down here. Here's the mean. Well, it's skewed positively. It's skewed to the right. But notice the mean is greater than the median. So the mean is always in the middle. So the median is always in the middle between the mean, median, and mode. If the mean is to the left, it's skewed left and negatively skewed. If the mean is to the right, it's positively skewed and right skewed. And the mode is on the other side because the median is always in the middle. Okay? Now, so that's the interpretation. So we're going to have a symmetric distribution, a negatively skewed distribution, and a positively skewed distribution. Now, outlier data points can have the same effect on the mean, median, mode by introducing skewness. So if I took this symmetric distribution and all of a sudden I move this 9 here, the value 9, if I move that one number out to 13, boom, it's going to be skewed right. If I took this distribution the way it is, I took this 3 here and moved it down to 1, boom, it's skewed left. So an outlier could cause skewness. One number can change the skewness of a distribution. Okay. The histogram. The next distribution. The next graph. It displays frequency content of aggregate numerical data. Okay. Let's take this data set right there. Now what I did, I took this data set and I rank ordered it. Rank order means you place it in order. It's ordered. So the rank order is 15, 17, 19, 19, 21, 22, 23, 26, 28, 32. It's from the lowest to highest. It's rank ordered. Now construct a histogram and a histogram requires 2 pieces of information. One, a starting point, let's say 15, and an interval, let's say 3. Now I selected 15 and 3. As it turns out, those 2 numbers are arbitrary. And we'll get into that here in just a second. First, construct a dot plot of the rank order data. Okay, let's do that. Okay, here's 15, 17, 19, 19, 15, 17, 19, 19. Here's 21, 22, 23, 26, 28, 32. And we can see this is skewed right. Okay, so we would expect the mean to be greater than the median. But we're looking at a histogram right now, so let's just look at the histogram. Okay, now the starting point is 15, so I started 15 here. Now my interval is 3. Now what a histogram does says, I'm going to start with 15, take an interval of 3, and I'm going to count the frequency in that interval. That's the aggregate frequency of numerical data in an interval. Okay? But when you start counting the data in an interval, you have an interval of 3. So 15. So you have 1, 2, 3. 15 is one end, 18 is the other end of that interval. When you start counting, you count the measure frequencies in each interval defined by the starting point and the interval. The interval frequencies include the lower value, exclude the upper value, and that's what that plus and 0 mean. In other words, our interval is 15, 16, 17, 18. We count 15, but we do not count 18. So the frequency is 2. So boom, the frequency is 2. The next interval goes from 18, 19, 20, and 21. We count 18, there's nothing there. We do not count 21. If we don't count 21, then the frequency is 2, and that's why there's a 2 there. So the next interval is 21, 22, 23, 24. We count 21, we don't count 24, so the frequency now is going to be 3, and that's why there's a 3 there. Okay, and then the next interval here is a 1, next interval is a 1, next interval is a 1. So the way that's represented, I'm going to come down here and actually, here's the intervals. I take these intervals 15 to 18 because my starting point is 15, my interval is 3, so I have 15 to 18, 18 to 21, 21 to 24. The interval is 3 on each one of those. Okay? And then in this interval, I have the numbers 15 and 17. In this interval, I have 19 and 19. In this interval, I have 21, 22, and 23. So this is the actual data. I count the frequency. There's two numbers. There's three numbers, 1, 1, 1. And this is what I plot in my histogram. Okay, so this interval has two numbers. I'll have 2. This is 2. This one is 3. This one is 1, 1, and 1. So this histogram with a starting point of 15, interval of 3, illustrates, let's back up here, the frequency content of aggregate data. And the data is numerical data. This is numerical data. And it's the frequency content of aggregate numerical data, because we aggregate it over the interval. Okay? So this is numerical data. And we'll look at categorical data later. But this is numerical data. Now, the starting point and the interval are arbitrary. Let's revisit that. Because let's go back to the rank ordered set here. What if I change my starting point instead of 15? Let's make it 14 and 3. If I did 14 and 3 and redid it, okay, now I have a histogram that looks like this. And look how that one little change from 15 to 14, notice how the histogram changes character from here to here. Big difference. It's not the same. I can also change the starting point from 15 to 9 and change the interval from 3 to 5. When it has a broader interval, I'll have smaller intervals, smaller number of intervals. And the frequency here, the histogram looks like this. Very big difference between this right here. So again, the starting point and interval are arbitrary. You can make this distribution pretty much look different ways. You can try different types, different parameters, starting point and interval, to have different looks. And so it's descriptive, but you're describing it different ways. Same data. Okay, now let's see how this can be used and misused. Okay, so the histogram illustrates a frequency distribution. The frequency distribution can be symmetric, skewed right, positive, skewed left, negative. Okay, from that, let's look at the use and misuse of histograms. We take the rank order data set, and there it is. On this side, we have the use of histograms. On this side, we have the misuse of histograms. Well, I consider it a misuse. We're doing the histograms as defined, but we're misusing those definitions, at least in my opinion. Let me show you. On the left-hand side over here, I'm taking a starting point of 9 and an interval of 5. So the interval is going to be 5 for all of these, but I changed the starting points. Nothing wrong with that. So here the starting point is 9. So there's my distribution. Boom, boom, boom. There it is. Now over here, my starting point is going to be 10 for all of these, but I'm going to change my intervals. But I don't just change the intervals for one interval. I change the interval for each one of these intervals. In other words, I change my interval as I go down. I think that's a misuse, because you can make it look any way you want. Well, almost any way you want. In this case, notice this goes 10 to 15, 15 to 18. This is 5, this is 3. I change the intervals, and so why? Because I get a nice uniform distribution. Is this really uniform? The histogram is. Are the data uniform? No, I don't think so at all. You can look at the dot plot up here, and that's not uniform. They're spread out. Okay, so look at the second one. Here I have a starting point of 6 and an interval of 5. When I compare this, I have the interval of 5, but I went from 9 to 6. And what happens is, here it looks like we have a fairly small variance. That's the spread of the distribution. So we have 1, 2, 3, 4. It's spread over 4 intervals. The interval is 5. Same interval, but here I have 1, 2, 3, 4, 5. So here I have 1, 2, 3, 4, and here I have 1, 2, 3, 4, 5, and the actual mode here, it's the mode, the highest frequency is much less because it's spread out. So does this mean the variance is larger? Well, yes, the variance looks larger on the histogram, but it's the same data set. But how can you misuse it? Okay, I started with a starting point of 10 again, but look what I did here. I changed these intervals. It looks like it's bimodal. There's two different modes. There's not one mode, there's two modes. How can you do that? I think that's misuse of the data. Okay, because I just changed the intervals here to count them the way I want to. So I guess make it look any way I want. Boom, 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 boom. So I guess I could call that gerrymandering, but anyway, you can make these look any way you want. Okay, not anyway, but almost anyway. Finally, this is interesting. My starting point, my interval is still 5, same as before, but now instead of a starting point of 9 or 6, I start at 10, and look what happens. It's still an interval of 5, but it looks like it's skewed right. But here, I have a starting point of 10, same starting point, very same starting point, but my intervals vary, and it illustrates a skewed left distribution. But again, the intervals are not equal, the same. I say that's a misuse. Anyway, so be very careful with histograms. Histograms can be very powerful to summarize data, to show the distribution, but do it responsibly. And when you look at histograms, ask questions. What's the starting point? What's the interval? Is it consistent? How did you measure? How did you plot the histogram, etc.? Okay, let's take the histograms one step further into a stem and leaf diagram. Okay, the stem and leaf displays the data points as the frequency content of aggregate data. So remember, a histogram is a frequency content of aggregate data. A stem and leaf is also the frequency content of aggregate data, numerical data. But they don't have bars, they display the data points. Okay, again, consider the data set, rank order the data, and create a stem and leaf with a leaf unit of 1. Well, what does leaf mean? Okay, suppose the leaf equals 1. Now let's take one of these numbers. Let's take this number right here, 5. Represent the number 5 as 0, 5. For a leaf of 1, the stem of 0, 5 then is going to be 0, and the leaf of 0, 5 is going to be 5. And so the units digit, a leaf of 1 is a units digit, that's 5. The stem is 1 to the left of the units digit. Since we're base 10, that's going to be 10. Well, let's look at the number 13. Well, represent the number 13 as 13. For the leaf of 1, the stem is 1, and the leaf is going to be 3. So the leaf, you have to identify the leaf in a stem and leaf graph. Whatever that leaf is, that's what you're going to be using to represent the histogram. So let's take this data set, the rank order data set, bring it down here, and notice how I do this. Here's the interval, and notice the intervals now. The starting point is 0. The interval is 2. Okay, we count the lower end, we don't count the upper. Okay, so let's take this data set up here, rank order data, and let's just list and just put it in the intervals, in the histogram. So let's here it is. Okay, 0, 1 is going to be in that interval. 2, 3, 3 is going to be in this interval. 4, 6 is there. 6, 8. 6 is going to be in that interval. 8 is going to be in that interval. There's nothing in that interval. 13 numbers in that interval, etc. The frequency, there's 2 numbers there. There's 3. There's 2, 1, 1, 0, 1, 0, 1, 0. Okay, so there's my histogram. Now the stem and leaf takes this histogram and represents it very differently. They still represent the histogram, but instead of bars, they represent it with the leaf part of the number. Okay, for example, these two numbers 0, 1, well, the stem of 0, 1 is 0, as we saw up here. The leaf is 0 and 1. So those numbers then become my histogram. What about 233? Well, the stem is 0 and the leaf is 233. Well, again, we have 4 and 5, and then we have 6, and then we have 8, and then we have 0. It's blank. It could be 0. It can't be 0. It's blank. So I leave it blank. So notice this right here, the numbers show us the frequency. 2, 3, 2, 1, 1. But what happens when you have 13? Well, the leaf up here is 1, so you only put the leaves here, and the stems are here. Well, the stem on this one is 1, and the leaf is 3. So I'm going to put 3 there as the leaf, and I put 1 here as the stem. Because there's only one number there. 13 is one number. And so that 3 here represents one number where the leaf is 3 and the stem is 1, so the number is 13. Likewise for 16, it's 1 and 6. So what you can see here, this is used for numerical data where we want to see how the leaf, this is the frequency. So we can see it's skewed right. But then they start with this as a representation of the histogram. But then they do something else. There are different versions of stem and leaf. This is the basic, my version, and the basic version. I list the midpoints. 0 to 2, the midpoint is 1, 3, 5, and 7. Now, the frequency here, view the frequency content using values in the histogram. That's what I did. Starting point is 0, interval is 2. I illustrated that. The stem and leaf frequency. This frequency right here. The stem and leaf frequency column represents the cumulative frequencies from the minimum to the median and the cumulative frequencies from the max to the median. So when we look at this, the way the stem and leaf will do it, it will identify the median. Okay, well, the median is in this interval. And there's a frequency of 2 in that interval. The frequency in parentheses is for that interval that contains the median. So this interval here contains the median. The frequency of that interval is 2 because there's 2 numbers. See the frequency, that's just the 2. But you go to the minimum, which is 1 down here. Go to the minimum, which is 0. And the frequency is a cumulative frequency from the minimum to the median. So here we have 2, I put a 2. Here I have 3. Well, 2 plus 3 then is 5. So this is cumulative all the way to the median interval. They go to the max. The max is 16. And then this is cumulative. 1, 0. 1 plus 0 is 1. 1 plus 1 is 2. So this is the frequency 2. 2 plus 1 is 3. 3 plus 1 is 4. So it's cumulative from the max to the median. So when you see these 3 frequencies, the interval that contains the median, there's 2. The frequency below or left to the median interval, there's 5 numbers. Above it, there's 4 numbers. So 5 plus 2, what is that? 5 plus 2 plus 4, add 3 numbers together, you get 11. That's the number, that's the sample size, or that's the population size, whether it's a sample or population. Okay, so 11 plus 1 is 2. 11 plus 1 is 12. Divided by 12 is 6. So the 6th order, 6th number becomes the median. So 5 and then 1 would be the 6th number. Well, 1 in here is going to be 4. So 0, 4 then we know is the median. So it tells you the median. But now that we have these, we can determine the mean, we can determine the different percentiles. And we'll do that down below in a minute. But now we have the median. Okay, so let's consider different stem and leaf examples with different data. But watch what I do here. I have the data over here, and I don't redo all of this. I just give you, and this is pretty much how it's done, they'll just give you the stem and leaf. So here's the frequencies. there's the stems, and there's a leaf. And so this is correct. But how do you interpret it? Well, the leaf is 1. That means 1 is in the units digit. That means the stem is 2. So the number is going to be 21. This is 23. What are those three numbers? 24, 25, and 25. It's those. What are those two numbers? What is that number? 29. And then that's 32. Okay, what's the median? Well, this is 3, 4, 5, 6, 7. 7 plus 1 is 8. 8 divided by 2 is 4. There's two numbers. That 5 right there is 25 is going to be the median. So this is leaf of 1. Let's come down here. A leaf of 10. Oh, so that 1, 3, 4, 5, 5, 9, and 2 is not in the units digit. It's in the tens digit. The stem is 2. If 1 is in the tens digit, then 2 is in the 100s digit. So that 1 represents 210. 1 is in the tens digit, 2 is in the 100 digit. This number here, since the leaf is 10, is 230, etc. Let's go the other way. What about a leaf of 0.1? Well, that is in the tenths digit, 1/10. Okay, and the stem is 2, which is in the units digit. So that number there is 2.1. And then 2.3, 2.4, 2.5, 2.5. Okay, one more thing that's important. The leaf is 10. So that number is in the tenths digit. That's in the 100 digit. So that represents 210. That's true. So the stem and leaf says the number is 210. Okay, fine. The number in the data set is 210. So it's a 1-to-1 matching. But what's this number? Well, the tens place is 3, which is 30. And the stem is 2, 100. This is 230. So the stem and leaf says 230. But the data set is 231. So it's not a 1-to-1 mapping. So the stem leaf says the leaf is the lowest discrimination that I'm going to represent. Below that, I'm going to ignore it. So it doesn't really illustrate the actual number in the data, because the data could be very different, 231 versus 230. But it represents the content or the information in that number that's valuable at this leaf of 10 level of discrimination. So 455, 240, 252, 253. And then 290, 291, 320, 324. So when you have a leaf of 10, then everything below that in the units digit on down is pretty much ignored or truncated. Okay? Okay, let's go on. Box and whiskers plot. Okay, now let's get into the percentiles. The box and whiskers displays the maximum, the minimum value, the first, second, and third quartiles. And so sometimes this is, I call it box and whiskers because you have a box here and you have whiskers on the either end. But some people call this just a box plot. But the way I'm representing it is what we'll use it in this course and the homework and the exams and everything. But it does illustrate 5 different measures. The minimum, maximum, first quartile, which is the 25th percentile. The median, which is the 50th percentile or the second quartile. And the 75th percentile, which is the third quartile. And it gives you 5 numbers. Okay, now, there's different versions of the box and whiskers plot. This is one version. There's all different kind of versions. This is only one version. You understand this, but be careful because people will use different versions of this. They'll start adding things to it because it's very descriptive. Very descriptive. There are no numbers in there. There are no numbers. Well, the only numbers you have is down here. But all it is just a graph representing the data. It just displays those numbers in a graph. Okay, so let's consider this data set, rank order it again, and there's the rank order. Okay, and then here's my data here, 0, 1, 2, 3, 3, 4, 5. I just list the data there. And then I say, here's the order. Now the order, that's the first number, second number, third number, fourth, fifth, sixth, up to the 11th number. That's the order of the number in that data set. The reason I did that is now we can say, oh, well, down here, the minimum is going to be 0. The maximum is going to be 16. There's the minimum maximum. I can take 6, here's my order. I can take 16 minus 0, the max minus the min, 16. That's called the range. The range is going to be 16 minus 0, which is 16. But then we can also calculate the median, which is the second quartile or the 50th percentile. They all mean the same thing. Well, 50th percentile means 50% of the distribution is that number and below. 50% of the distribution is that number and below. And 50% is that number and above. Okay? Well, as it turns out, the logic behind this, there are 11 numbers. To get the 50th distribution, you're not looking at just the numbers. The numbers are like the center of an interval. And so the center of an interval starts a half an interval below and a half an interval above. And so essentially there are 12 different intervals. So between 1 and 2, there's one interval, 2, 3, 4, 5, 6, 7, 8, 9, 10. But 11, the interval above that is going to be 11. Below 1 is 12. So there's 12 intervals. In other words, to get the 50th percentile, I'm going to take 50% of 11 plus 1 because there's 12 intervals. 11 plus 1 is 12. Half of 12 is 6. That's the order at which the 50th percentile or the second quartile or the median occurs. Okay, so the sixth, 1, 2, 3, 4, 5, 6 is right here. Well, that's the order, the 6, but the data then is 4, so that right there represents the 6th ordered number in the data set, and so that becomes my median, my 50th percentile, my second quarter. So I'm going through this in detail, but hopefully it helps. So Q2 then equals 4. What about the 20? Now I can do different percentiles. What about the first quartile, which is the 25th percentile? The 25th percentile over here. Well, 11 plus 1 is 12. 1/4 of 12 is 3. The third number here is 2. So 2 becomes my first quartile. Boom, and there it is. What about my third quartile? Well, 75% of 12 is 9, and the ninth order, the ninth position is 8. So then 8 now, 8 becomes my third quartile. Now, we have a range up here of the data. But if you take the third quartile and you subtract the first quartile, in this case, it's 8 minus 2. That difference is 6. That's called the interquartile range. So the range of the data is the difference between the max and the min. The interquartile range is the difference between the first and third quartiles. And so those two are used as a measure for all different kind of descriptive purposes. Now, here I allude to how you calculate it, but down here I go through the 25th, 50th, and 75th in detail. Okay? But the reason I do that down here is now we don't have to have 25, 50, and 75. I got to have different percentiles, like the 10th percentile and the 90th percentile, or even the 78th percentile. Okay? Well, the 10th percentile here is just 10% of 12 is 1.2. Oh, now I want the order, the 1.2th order, if that's a word. Well, it's going to be 1.2 is between 1 and 2. It's 20%. It's 20% of the way between 0 and 1. So I'm going to have 0, which is the first one, which is the first order, and 20% of the way between 0 and 1, or 1 minus 0 is the interval. That's going to be just 0.2. What about the 90th percentile? Well, 90% of 12 is 10.8. Oh, so it's between the 10th number and the 11th number. It's 80% between the 10th number and the 11th number. Well, the 10th number is 13. The 11th number is 16. I want 80% of the way between those two numbers. So I bring 13 down. There's 13. I want 80% of the way between 16 and 13. Well, 16 minus 13 is 3, and 80% of the way times 13 is 15.4, and there's my 90th percentile. Okay? And then finally, what's the 78th percentile? Well, you can go as detailed as you want. 78% of 12 is 9.36. So between 9 and 10, it's 36% of the way between 8 and 13. So I bring down the 8. 36% of 13 minus 8 is, whatever that is, 5. And that turns out to be 9.8. So given the order here and these numbers, we can calculate any percentile we want. But we don't put it in the box and whiskers plot. The box and whiskers just gives you those three along with the max and min. So for this distribution here, my box and whiskers looks like this. So you can tell it's skewed right. It's positively skewed. If it's symmetric, it's going to look like this, nice and symmetric. A box with equal whiskers on either side. If it's skewed right, you'll have a box with a longer whisker on the right side. So that's a skewed right distribution. If it's skewed left, you'll have a box, you'll have a box with a longer whisker on the left side. So it just tells you the skewness. And the box and whiskers plots are very popular to illustrate data. Very popular. Okay, let's go on. Bar chart. Okay, now we're displaying frequency content. Now we're moving away from numerical data to categorical data. Okay, so now I'm saying here's the number of injuries in a department. Say they consider the number of injuries in a department. So you're tasked with looking at the number of injuries in the different departments of this supermarket, let's say, or let's in this department store, in a very large department store. Okay, so we've measured over a period of time. Here's all the numbers. Okay, well, let's actually represent this. Let's plot this with these departments. Now, these departments' ID are numbers. They don't have to be numbers. They could be this department, that department. They could be names. They could be IDs. They could be XY department, A department, L-3 department, the purchasing department, or the distribution department. They could have numbers. That's what I mean by categorical data. But then I do the histogram. This time the bar chart is a histogram of categorical data. So I have the numbers here. That's the frequency. But over here, these are not necessarily numbers. They are, but they're really categorical. So they're coded. They're departments, but they're coded with numbers, which we saw in the introduction. And so there it looks. Okay, so that's a bar chart. Because, well, you know, some of them have low, some have high. Okay, there's 30 different departments here. Wow. You know, let's pull out the ones that are problems. There's a number of them. How many are of them? I don't know. We have to. Well, sometimes when you're doing an analysis, you're given data set, and you can create a histogram, but you might, instead of saying 30 departments, you might have 300 departments, and there might be quite a few problem areas. Let's do the worst ones first. Let's do the departments that have the highest frequency first. Well, there's where we come to a Pareto chart, or a Pareto analysis. It displays frequency content of categorical data just like a bar chart, but it's rank ordered by frequency. I took the same data set, the very same data set, but then I rank ordered it not by department, but by injuries. So now we can see 1, 2, 3, 4, 5, 6. We have 6 departments out of the 30 that are a problem. And department 13 is probably where we should start. Okay? But 13, 7, 25, 29, 18, and 30, those are the ones we probably should be looking at. Let's start with 13 because that's the worst. Because if you start with the worst one, you get that solved, you're going to solve a lot of problems on the very beginning. And if you're solving problems or you're doing a Pareto analysis, this is extremely useful, extremely powerful, because when you start a project, you want to cover as much ground as you can at the beginning, because then you get a momentum. If you have if you cover small amounts of ground, that momentum's hard to gain. It's hard to possess and franchise your team. But if you do 13 first and you get a lot of success, if you solve a lot of injuries, then you get a momentum going, and before you know it, you're done with 80-90% of the job. Okay, let's go on. A pie chart. This is relative, again, categorical data, but it's a relative frequency count. It's relative frequency, not absolute. Okay, the idea here, let me illustrate what a pie chart does. I'm sure you're used to a pie chart, but let me develop this to show you what it does and what it doesn't do. Okay, suppose we have a budget, two budgets. Budget 1 was 1 year, budget 2 was the next year, let's say the following year. And so these are millions of dollars. A, B, C, D have $12,643 million. So their total budget was $25 million. Now budget 2 was 8,421. The budget was $15 million. They cut the budget. Well, when you start cutting your budget, you start worrying about, oh, okay, oh, wow, is that a problem or what? Or let's say that budget 2 was last year, budget 1 is this year. We've increased the budget. Oh, that's nice. Okay, but if you do a histogram, which I did here, here's budget or a bar chart. Here's budget 1. This is the bar chart. Budget 1, budget 2. Okay. And they look pretty much the same. A, B, C, D, A, B, C, D. Oh, well, the budget's less, the budget's more, but we distribute them pretty much the same way. The shape looks about the same. But then the question is it the same? No, I think it's different. How can you tell? Let's don't look at the bar chart of the frequency. Let's look at a pie chart of the relative frequency. Okay, so down here when we do budget 1, we can see that budget 1, Department A has 48%. In budget 2, Department A has 53%. So, oh, they have less. Yeah, they have less, but they have a higher percentage of the total. So, oh, our budget decreased. Not really, your budget increased relative to the entire budget. It did decrease relative to the absolute value, but it increased to the relative value of the total budget. Okay, and then Department D, okay, they went from 12 down to 7. So A increased in percentage, relative percentage. D decreased in relative percentage. So D says, "Oh, hey, wait a minute, we're getting less budget." Well, he says, "Yeah, so did we. We all got a decrease." Well, what instead of doing it this way, what if they did it with the pie chart with relative frequencies? And then D says, "Yes, but we went from 12% down to 7% of the budget. A went from 48 to 53% of the budget." Okay, so which one is right? They're both right, but you're looking at it different ways. Now, sometimes these bar charts they're put together, they're combined. I call it a donut chart. People call this concentric pie charts. They're done different ways. Now, it's all relative. Okay, but really it's relative to the budgets. Well, budget 1 is the inside pie chart or concentric circle or donut. Budget 2 is the outside. So you can see the relative difference here. A here has a higher percentage of the total than the budget 1 does. Right? And budget 2, you can tell the differences. Okay, some people like this. Okay, then there's a radar chart. Now the radar chart displays multiple variables. And notice this is categorical again, but I have budget 1, budget 2, and budget 1 and budget 2 together, but I can put both of these together with the departments and represent them with multiple variables. Instead of looking at budget 1, budget 2, I'll look at A, B, C, and D. For example, budget comparisons for departments A, B, C, D. So I'm not just comparing the budgets, I'm comparing the departments. So it's a little bit different comparison. So departments A, B, C, and D, we see here that, and also this axis here are the budgets. Okay? And so A has 12, and B has, B has 8. So you can see here how the relative difference here has decreased. The budget has decreased, but here's how they've decreased from the budget 1 to budget 2. And some people like radar charts, and sometimes they're easy. Well, radar charts are valuable where you have 5, 6, 7, 8, 10, 12 different variables you're looking at. And so you look at a variable, and then it changes, it changes, it changes. Well, you can see right here, the changes, relative changes, A still has the greatest dollar value of the budget. Okay. Again, this is introducing it. We're not going into too much depth because we have a couple more to do. Line chart and a control chart. A line chart displays the data in the series, displays the time series data, monitor a process. Now, this is constructing a simple process control chart. Essentially, what I'm doing here is I want to construct a line chart. But the line chart will have a center line, which is the mean of this distribution. Okay, and the mean is going to be 5. But I want to plot it, but I want to plot a line chart with the upper control limit to be, where's it at? Here it is, 3 times the standard deviation of the mean of that sample. Okay, and so what I'm going to be doing here is saying, I tell you what I'm going to do. I'm going to take the sample size of 8. This is 8. The mean is 5. I took the mean. And the variance is 2. But the variance is divided by n, a population variance. Okay, so then I take this control chart down here. And the standard deviation of the mean is the square root of the variance of the mean. Well, the variance of a mean is the variance of the variable divided by n. So this variance of 2 is the variance of x. It's the expectation. It's the second central norm of x about the mean. Okay, but the variance of a mean is the second around of the mean. Okay, we want the variance of the mean. Well, that's going to be over n, divide by n. Okay. And I don't derive that, but I'll just say that. Okay. So let's plug and crank. The mean here is 5, bring down the mean. 3, the standard. The square root of variance over is 2 over 8, which is 3/2. And there's my upper and lower limit. So I pull these down here. So it says, I want to do a line chart. But the line chart is going to be plotting the values to where if the values go above 6.5, I'm above 3 standard deviations of this center line, of the mean of this sample here. If it goes below 3.5, I'm below 3 standard deviations of the mean. So when I start plotting things down here, I go, here's my plots, bing, 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 I plot, dot, dot, dot. The dots are well within 3 standard deviations of the mean. So when you start plotting a line plot, sometimes you want to interpret it. You want to evaluate. Well, the control chart is one. And you'll see the control chart more in operations and quality control. Okay. I think the last thing we're going to do is a scatter plot. This displays the relationship between 2 numerical variables. Okay, here I have 2. Now notice that this is a paired set of data. So these are the indexes, and it's a paired set. Like this is person 1 did 3 and 25. We've done that in other videos. Person 2 has 5 and 36. Person 3 has 6 and 37. So we want to plot x versus y. So if we do that, and we bring this down here, here are the x's, 3, 5, 6, 7, 8, 8, and here are the y's, 25, 36, 37. I plot them, and there they are. So the scatter plot, which we've already seen in other videos, I'm doing it again here just to be complete. Here is one variable represented with another variable. And from this scatter plot, bivariate measures, we can do the regression line, correlation, covariance. We'll do that later. Okay, but from this data, we can visualize It's a positive correlation. It's a positive regression. It's 0.98. It's a pretty high correlation because all those numbers, the variance around some regression line is pretty small. Is that we'll talk about that a lot more later, and I'll show you a lot of different examples of different correlation values and what they look like. Okay, and so here's a scatter plot, and then I do a summary again. This is what we did today for this last hour and 10 minutes. We went through all these distributions, describing them, and the homework is this is going to be one question on just say, if you're displaying the frequency kind of aggregate numerical data, what kind of chart is it? It's going to be a histogram. You just match them up. And mainly that question, the homework. But anyway, this is the summary of what I did today. And that's all I have for today with descriptive statistics, with graphs and measures, okay, with percentiles and everything. That's all I have. And so that is going to be an introduction to descriptive statistics, which is very powerful and very useful in business. That's all I have for today. Between now and the next time I see you, I hope this helps, and stay safe. Take care.